Thank you for the introduction, and I would like to thank the organizers for the opportunity to be on this conference and to be in this nice city. My talk is devoted to some bounds for the error of sampling discretization and some corollaries from this. First of all, I recall what is the problem of sampling discretization. So assume we are given with two constants. We consider some n-dimensional subspace, so capital L will be always n-dimensional subspace of continuous functions, and we consider integral LP norm with respect to some probability measure on some compact set on n-dimensional subspace, or just compact set in metric space. And we consider the problem of sampling discretization. So we are asking for how many points do we need in our set such that we can replace our integral norm, integral LP norm, with the discrete one. And we will be most interested in the situation when weights are equal, but we can consider a generalization when weights are not equal, but in my talk we will consider mostly equal weights. Obviously, the number of points cannot be less than the dimension of the subspace, and basically we are asking ourselves under which conditions on the subspace we can choose number of points close to the dimension, or to other parameters of our problem that we will see later. Another modification is discretization with epsilon. In this case, we are interested in almost isometric replacement of LP norm with discrete one. And I will mostly consider the case with epsilons. So, first results of such kind are due to Marcinkiewicz and Marcinkiewicz-Zygmunt for trigonometric polynomials, standard one. So if you consider standard set of trigonometric polynomials with frequencies in the given interval, then you can discretize LP norm when p is between 1 and infinity, excluding 1 and infinity, with some constant dependent only on p, and the number of points is just the dimension. If you want to discretize L1 norm or L infinity norm, you must take slightly more than the dimension, but like 2 times the dimension will do, and this is the result for trigonometric polynomials for the standard one. These are old results, and we are interested in general case, general situation. The important assumption on the subspace that will play a crucial role during my talk is Nikolsky type inequality assumption. So we say, we say that the subspace L satisfies Nikolsky type inequality assumption with some constant, which obviously depend on subspace, on dimension, on Q, if we can bound L infinity norm with LQ norm multiplied by this constant. And we need this bound for every function on our subspace, right? This is a notation, and I will be most interested in the assumption to infinity Nikolsky type assumption, because in this case the estimate can be easily checked. Infinity to Nikolsky type inequality assumption is equivalent to the bound for sums of squares of your orthonormal basis in your subspace. This pointwise bound is equivalent to this Nikolsky type inequality with Q equals 2. For example, trigonometric polynomials, multidimensional, with frequencies, with any set of frequencies, satisfy this condition with h square root of the dimension. So you should think that h is something like square root of the dimension in our considerations. What is known in general situation for LP? Under the Nikolsky to infinity Nikolsky type inequality assumption, with the constant exactly square root of n multiplied by some constant, we know that we can discretize LP norm on any subspace satisfying this assumption with a number of points bounded by this quantity. So what is this? This is n when p is between 1 and 2, and p over 2 when p is greater than 2. And some logs. We know that when p is 2, we can remove this log, more or less. In other situations, we know that there are some powers of logs, but mostly logs. And the important observation is that under this assumption, the number of points must be at least n to the power p over 2 when p is big. So there is an example. For every p over 2, we can find a constant such that we can find an n-dimensional subspace satisfying Nikolsky type assumption, and such that the discretization inequality implies lower bound for the number of points. This is a simple observation, but it is important for us. Okay? So how we would study the discretization problem? We will consider the error of sampling discretization. So we fix a set f of continuous functions. For example, it is LP ball on some subspace, but currently we do not have any assumptions on this set f. And we consider for the fixed set of points, we consider the error of discretization. So this is just the worst case error. And we are interested in the quantity which is the infimum over all set of points. But we will mostly consider the construction of these points due to the random choice of these points. So basically, we consider x1, xm identically distributed independent random variables with distribution mu. This is our measure on our set. And simple observation is that the infimum is bounded by the mean value. So we will try to control the mean value of our error when the choice of points is random. I recall some definitions about the chaining functional. So if we are given with a set, any set, we consider on this set increasing sequences of partitions. So the next partition is some subpartition of the previous one. And such that we control the number of sets in each partition. For any function f from our set, fn of f is the unique element of this partition where f belongs to. And we consider gamma 2, which is called the chaining functional. So basically this is this infimum, and infimum runs over all admissible sequences of f. Admissible sequence is defined here. So here is a partition. We consider the diameter, multiply by this 2 to the power n over 2, taking supremum over all functions and trying to find the best possible partition. It will be needed for the next slide. So this is the result of Guidon, Mendelssohn, Pajor, Tomchak, and German. Basically, this is not very hard result, but basically they bound the error in L2 case. So the bound is this. You consider any set of continuous functions, and this is important. The set is arbitrary. And we consider, as I already told, the random choice of points. Then the expectation of our error is bounded by this quantity, where A is 1 OM multiplied by the expectation of this square of gamma functional with respect to the random metric. This random L infinity discrete metric. And this is L2 case. What we can do for other P? Rather silly observations that we can consider sets of this form. So if we are given some set f of continuous functions, we can consider new set G, which is f to the power p over 2, and we can plug in this set G here in this theorem. Another question, how we will control this gamma functional, but it is known that you can control by a simple Dudley entropy bound. So the gamma functional is bounded by this sum of, basically the sum of entropy numbers. And what is entropy number? This is the definition, but basically you want to cover your set with, you're asking yourself, what is the minimum radius of a ball such that you could cover your set with 2 to the power n balls of this radius. So it is some measure of compactness of the set. So what we are doing now? We are taking this theorem, we are considering this silly set, and using Dudley entropy bound. And this gives us a bound for any p. So this theorem, for any p between 0 and plus infinity, any p, we can bound the expectation of our error of sampling discretization by this quantity, where a is quite big thing, but I have bound the gamma functional by this series of entropy numbers. So when p is bigger than 2, here is 1, and here is some factor. But when p is less than 2, there is none of this, but here are powers p over 2 of these entropy numbers. This is rather general theorem because set f is arbitrary. And we now can try to plug in different sets. Well, let us test this theorem for universal sampling discretization. So I recall that the setting of universal sampling discretization was described in the talk of Professor Feng Dai. Basically, we want to discretize LP norms for a set of subspaces. And our set of subspaces is this. We are given with some basic functions, G1, Gn, and we consider all subspaces spanned by V functions from this collection. And we want to obtain a discretization result for any function from this, from any of this V-dimensional subspace. So this theorem, we consider arbitrary p between 0 and 2, arbitrary error. We are given with a set of basic functions. We assume that they are bounded, and we have this condition. I point out that this condition implies inequality type and equality assumption, so this is a crucial thing. Then we can obtain discretization result just using this general theorem and some bounds for the entropy numbers. We can obtain that we have a discretization result with a number of points bounded by this. So this is a big thing, but let us compare with the result from Professor Dai talk. Professor Feng Dai and Professor Temnikov managed to prove the similar result when p is between 1 and 2. And instead of this thing, they have log kv squared and this to the power 1. So basically the difference, I can write it down. So instead of the thing that is there, they have this thing. So instead of this cube, they have this thing. So the result is better in terms of the dependence on n. But this result is valid for p, every p between 0 and 2. And the result is for p between 1 and 2. But I think the method should work for other p also. And here is better dependence on epsilon. And this result is more or less free, because we just have used this general theorem and some known bounds for the entropy numbers. Okay, this is what we have for universal discretization. Let us move on to Orlicz things. So let me return for a second to these known results for LP balls, for just discretization in LP. So we see that there is big difference between situation when p is less than 2 and when p is bigger than 2. And the interesting question, how we transmit from the situation when p is less than 2 to the situation when p is bigger than 2. Because after p is bigger than 2, we must have polynomial growth. And to try to answer this question, one can consider Orlicz spaces. So I will have a formal definition here, and then I explain what is written here. This is a definition of almost increasing or almost decreasing function, but it basically means that your function is increasing if you multiply here by some constant bigger than 1. If a is 1, it is just increasing function, and here we are helping our function to be increasing and multiplying by some constant. This is equivalent to the assumption that your function is between two increasing functions. And another definition is this. So phi is increasing p if this quantity is increasing. Phi is almost increasing p if this quantity is, if this function is almost increasing. And the same for decreasing. So phi is decreasing q if this function is decreasing. Phi is almost decreasing q if this function is almost decreasing, with some constants here. But what does it mean? Basically, we want to relax the convexity assumption. So you probably know that Orlicz spaces works with convex functions, and convex functions are like this. So for convex functions, we know then that when we divide our function by t, it is just an angle and it is increasing, right? And basically this is some attempt to relax the convexity assumption. So instead of convexity, we assume that phi t over t is increasing, and when we assume that phi t over t to the power p is increasing, basically means that we try to relax the assumption that p root of our function is convex. So basically all of this is some relaxation of convexity or concavity of a function. For simplicity, you can always assume that function is just convex, or the p power of a function is convex. The functions that we are considering are these. So they are increasing, like on the picture. They are 0 at 0 and continuous, and at infinity they are infinite. So basically functions of this type. And as I said, we are considering functions that phi t over t is almost increasing or just convex. So the first condition is relaxation of convexity. The first one we are calling like phi functions, and the second one convex phi functions. Simple example, this is our t over p with some logarithmic term. So basically, this function should give us LP space, but something bigger than LP space. logarithmically bigger than LP space. And some simple computations show that this function is increasing p and decreasing with some p plus alpha plus beta. This will be our model example in Orlicz case. So I recall just the definition of Orlicz space, of Orlicz norm. We again given with a probability measure on our compact set. We're given with a phi function. We're considering this function on rho phi. And we consider the space of all functions such that this assumption is true. And we consider the so-called Luxemburg norm. It is basically a Minkowski functional generated by this set when, like, by set rho phi less than or equal to 1. It is called a Luxemburg norm. So this thing is a norm when the function phi is convex, and it is a quasi-norm when we consider just a phi function, a relaxation of convexity. Quasi-norm means that we have all the properties of the norm, and triangle inequality is replaced by triangle inequality with some constant. Okay, so this is the setting. What do we know? Again, we're using this theorem for L2 space, this general result, and plugging in a very silly set, this one. We put in this set in the theorem and obtain a general result. We are given with a p and q. We consider a function, phi function which is almost increasing p, decreasing q. And then for any n-dimensional subspace satisfying Nikolsky assumption, we can bound this expectation of our error over L phi ball on our subspace, right? And the bound is again involves some quantities dependent on our function phi and the expectation of this sum of entropy numbers. And we moved from the entropy numbers for L phi balls to the entropy numbers of LP balls because we have this assumption. So it allows us to replace L phi balls with LP balls here. For LP balls, we know bounds for entropy numbers, and we can derive some results from this general statement. So, this is just a lemma that tells us that indeed, if we can bound this supremum, then we have a discretization result. So basically, it states that under some standard assumptions, if supremum is small, then we have a discretization bound. And here you should assume that nu is discrete norm. But the result is just general lemma. So what is the corollaries? Again, for any p, for any phi function satisfying some almost increasing p assumption and some decreasing assumption with some q, we can find the constant such that we can discretize L phi norm. So we replaced integral L phi norm with the discrete one, and the number of points is bounded by this. So, example, our model example, we are considering this t to the power p with logs, and we get a discretization result with the number of points exactly n to the power p of this minimum. So it is again 1 when p is between 1 and 2, and p over 2 when n is bigger, when p is bigger than 2, and some logs. So here is our transition. So when p is 2, here is our transition from L2 case if we consider t to the power 2 with logs. So here will be n, and these logs, they are growing with alpha. This is example of application of our theorem. Another interesting question is one-sided bounds. So Professor Craig in his talk mentioned the result, which is this. So for LP norm, we can bound integral LP norm with discrete L2 norm, and here is a factor n to the power 1 over 2 minus 1 over p. And we wanted to generalize this result, and the generalization is this. So again, we consider Orlicz space when our function is almost increasing p, no decreasing assumption. Then we can bound Orlicz norm with integral Orlicz norm with a discrete L2 norm, and here is the quantity which will be exactly this when phi is t to the power p. And it seems that this result could be slightly generalized, as we discussed with Professor Mario Ulrich. It seems it could be generalized, but I haven't write it down, so I presented the result that we checked. That should be correct. Okay. So this is a discretization result. How can we use it? Firstly, example. Again, we consider our model example, t to the power p with logs, and we have a one-sided discretization bound of Orlicz norm by L2, discrete L2 norm, with the constant exactly this n to this power and logs, some logs. And how it could be used? It is known that when we have one-sided bounds, we can use them to obtain some recovery results. So I just recall some terminology. We consider the sampling number, they are called, I think, linear sampling numbers, for a functional class f. So we are trying to recover our function with respect to some norm by linear methods of recovery, and what we are given with function values. So we are trying to recover our function using only functional values and linear methods of recovery. And we try to compare this recovery, sampling numbers with Kolmogorov-Witz. So the Kolmogorov-Witz is just the best way to approximate your set with linear subspaces, with n-dimensional linear subspaces. And Vladimir Temlyakov managed to prove that in L2 case, you can bound sampling numbers by Kolmogorov-Witz with respect to L infinity norm, and here we consider recovery NL2 norm. Again, in the yesterday talk of Professor Craig, we saw that we have a similar thing with some factor for recovery NLP norms when p is bigger than 2. So again, we can bound sampling numbers, linear sampling numbers with Kolmogorov-Witz, and here is some factor dependent on the dimension, on our parameter, or here on the dimension of subspace. We managed, having one-sided bounds, it is simply to get a recovery result, and the recovery result for Orlicz norms is this. So again, p between 2 and infinity, we consider almost increasing p functions, and we can bound the sampling numbers, Cn, with Kolmogorov numbers with respect to L infinity norm, and we try to recover in Orlicz norm, and the factor is this thing from one-sided bound. One-sided bound here. So, example, we are again substituting this function and obtain this n to the power, like here, and some logarithmic terms. The interesting thing when p is 2, when p is 2, we have a recovery result in Orlicz space with norm stronger than L2, so logarithmically stronger, but still using linear methods of recovery. We're interested in linear methods here. And here appears only a logarithmic term. So for L2 norm, we know that nothing here is needed, and for Orlicz space, which is L2 multiplied by logarithms, we have obtained here a logarithmic term. So returning to one-sided bounds, we can now speak about bounding our Orlicz norm with by discrete Orlicz norm. So earlier we consider bounds of a Orlicz norm by L2 discrete norm. Now we want to bound Orlicz norm by Orlicz norm. For example, in LP case, we often try to bound integral LP norm by discrete LP norm. In Orlicz case, we do not know how to do this, but we have this result. So P is arbitrary. We have two Orlicz functions, which is increasing P, decreasing with some Q, and we assume that our phi can be bounded in terms of psi in this way. And we also assume that this technical assumption that this supremum is finite. Then we can bound integral Orlicz norm with the discrete Orlicz norm, and here is some term dependent on M, but actually on the dimension. So here is L is arbitrary subspace without any assumptions, no Nikolsky assumption, and previously it also was like this. So let me mention this. But here are no assumptions on the subspace. Subspace is arbitrary. And again, here subspace is also arbitrary and dimensional subspace, and we replaced Orlicz norm with Orlicz norm, and the number of points is like this. And here is some term, but let us consider an example which shows like what it actually means. So we have our model example, and we have this estimate when alpha, beta, and beta are equal. So one of our assumptions is satisfied, the second one trivially is satisfied. So we have this result. For any n-dimensional subspace without any assumptions, we can bound integral Orlicz norm of this type by discrete Orlicz norm with 0 beta, but alpha replaced with 2 alpha. The number of points again is n with some logs when p is less than 2, and p over 2 with some logs when p is bigger than 1. And we can we have this bound with term which is logarithmic in the dimension. And we do not know how to obtain a bound without this logarithmic term. For example, can we replace integral Orlicz norm with discrete one with the same Orlicz functions? We do not know this. So some literature. My talk was based on two works. First one with Professor Sergei Tikhonov, which is on archive. The second one with Professor Vladimir Temlyakov, which is work in progress, but I think soon it will be on archive. This is a paper with this theorem that I have used. These are two papers that studied universal sampling discretization, a book about Orlicz spaces, the papers that have this nice recovery result in L2, the papers that of Professor Craig Požarsky, Mario Ulrich, and Tino Ulrich that have been mentioned yesterday, and this is just a survey that you can use to study our progress in this type of results. So thank you for your attention. If you have any questions, I will be glad to answer them.
Concerning discretization in LP for P larger than P,
yes.
the general subspace of dimension n, so the number of points is n to the p over 2 with some log factor.
Yeah.
So for P, I just want to say that for P an even integer, you can remove the log.
Yes, yes, I see. Yeah. Thank you.
Regarding the sharpness of your results, do you know if the factors are optimal for general Orlicz functions? And if not, just as a question for us, it's always the Sobolev space with p equals 1 that is the worst input class, so to say. Are maybe these numbers known for approximation in Orlicz spaces? Do you know that?
No, I don't know. Which numbers? Which numbers are you speaking of? Which numbers?
For the sampling. With the sampling.
I mean.
The discretization result is by sampling, and
yeah.
we prove that our results are sharp because the sampling numbers are known for the Sobolev classes, right?
Yeah. I don't know. We haven't checked this. This is an interesting question. Yeah.
This is known, right?
Mm-hmm. Yes, I don't know. I don't know. This is a very interesting question. Yeah. Yeah. I don't know how sharp they are.
If p less than 2.
Yeah.
And alpha is very big. Your dimension of number of points became maybe too big, because in this case it's you already. What is the result for p less than 2?
For p, yes, yes. For example, this one. Yeah. This is also a very interesting question, because we know that for LP spaces, when p is between 1 and 2, we do not, like log to the power 3 we need, or just less. But yeah, this is a very interesting question. Do we need this log alpha when p is between 1 and 2?
Power.
Yeah, exactly. But we don't know. I mean.
I don't know what about.
But it's a very interesting question. Yes.
For Banach space, maybe Gideon.
There is a log.
Unknown.
There is a log. What is the power? I think
power. If you have Orlicz space of this type.
I don't know for Orlicz space.
Okay. Thank you.
Yeah, but the question is very interesting. Yeah. Okay. Thank you very much.